In this lecture, I answer two questions. In the first question, we find out the area of this pentagon ABCDE, and in the second question, we find out the area of this ring shape. So we start with the first question. In the drawing, we have pentagon ABCDE. What is a pentagon? A pentagon is a flat, closed shape with 5 straight sides and 5 interangles. This is pentagon ABCDE. It has 5 sides, 1, 2, 3, 4, 5, and 5 interangles. 1, 2, 3, 4, 5. So, in the drawing, we have pentagon ABCDE. Note that those two angles are both right angles. This is side ED equals to side EA equals to side EB. They are both equal to 1 unit in their lengths. DC equals to X, AB equals to 1 minus X. Again, our test is to find out the area of this big pentagon ABCDE. So first of all, we join points E and B together by a straight line. And we join points E and C together by a straight line. In the next step, we'll extend side BA of this pentagon ABCD in such a way that the extended part will be equal to X units in its length. We define this point as point M. So actually, the extended part AM is equal to X units in its length according to our construction. BA is one side of the big pentagon ABCDE, and therefore it is absolutely a straight line. We extended the straight line BA by a straight line, and the result is BM. When you extend a straight line by a straight line, the result must be a straight line, and therefore BM is a straight line. If you focus on the upper side of the straight line BM at point A here, the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BM at point A? We have this angle that is the right angle, plus this missing angle, so that must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Next step, we join points E and M together by a straight line. By joining points E and M, we created here the right triangle EAM. So in the next step, we will prove that those two right triangles can join to each other according to side angle side rule. That is to say, we prove that the right triangle EDC can join to the right triangle EAM according to side angle side rule. So right along, we have to prove that the right triangle EAM can join to this right triangle EDC according to side angle side rule. So why those two right triangles can go into each other? First of all, side AM or side EAM is equal to side DE. They are both equal to x and therefore they are equal to each other. So write it down. AEM equals to DC. And again, if you found out that side AM or the right triangle EAM is equal to side DC or the right triangle EDC, they are both equal to x and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So here this is again EAM. In the right triangle EAM, and it is equal to this again EDC. In the right triangle EDC. Okay, again, if you found out that angle EAM in the right triangle EAM is equal to angle EDC in the right triangle EDC, they are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides, they are both equal to 1 and therefore they are equal to each other. That is to say, side EA of the right triangle EAM is equal to side DC of this right triangle EDC. So if it again, if you found out that side EA in the right triangle EAM is equal to side DC in the right triangle EDC, they are both equal to 1 and therefore they are equal to each other. So if you found out that those two sides and the angle that is included between those two sides in this right triangle EAM are correspondingly equal to those two sides and the angle that is included between those two sides in this right triangle EDC. And therefore those two right triangles can go into each other according to side angle side rule. So triangle EAM congruent. This is the sign of congruent to triangle EDC. According to side angle side rule. And again, we have those two sides and the angle that is included between those two sides in the right triangle EAM. They are corresponding congruent to those two sides and the angle that is included between those two sides in this right triangle EDC. And therefore those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we will derive two things. The first thing that we will derive that they have also the same areas. That is to say, the area of this triangle EAM is equal to the area of triangle EDC. Or of course, any two triangles that can go into each other, they must have also the same areas. So, the area of the right triangle EAM is equal to the area of this right triangle EDC. Again, the area of triangle EAM is equal to the area of triangle EDC. The second thing that we will derive from the fact that those two right triangles can go into each other, we will derive that EC equals to EM. EC equals to EM. EC equals to EM. This is side EC equal to side EM. So all those two sides are equal to each other. Are equal to each other according to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles can join to each other, and therefore those two corresponding sides must be also equal to each other and their lengths. So actually found out that this is the right triangle EAM, or the area of this right green triangle EAM is equal to the area of this triangle EDC. Because they can go into each other, and therefore they have also the same areas. Those two triangles have the same areas. So if we define the area of this right triangle EAM as Z, that is to say the area of this triangle EAM is equal to Z squared in its size. Then the area of this right green triangle EDC must be also equal to Z squared in its size because they have the same areas. In the next step, we find out the length of side MB. MB in total equals to MA plus AB. So as you know, MB equals to MA plus AB. So MB total equals to MA is X plus AB is 1 minus X. So the total MB equals to X plus 1 minus X. X minus X is 0, therefore we left only with 1. MB equals to 1 unit in its length. MB equals to 1. In the next step, we will prove that those two triangles can go into each other according to side rule. That is to say, we will prove that this triangle EMB can go into this triangle EBC according to side rule. So, write it down, we have to prove that this triangle EMB can go into this triangle EBC according to side rule. So, why those two triangles can go into each other? First of all, we have already found out that EC equals to EM or EM equals to EC. Those two sides are equal to each other. So side EM or triangle EMB is equal to side EC of triangle EBC. And again, side EM of triangle EMB is equal to side EC of triangle EBC. In addition, we already found out that MB equals to 1, and it is equals to BC, this is also equals to 1. So MB side MB of triangle EMB is equal to side BC of triangle EBC. And again, side MB of triangle EMB is equal to side BC of triangle EBC. They are both equal to 1 and therefore they are equal to each other. And finally, EB is a common side that belongs to both triangles. It is very easy to see that EB belongs to triangle EBM and EB also belongs to triangle EBC. So can I know that EB equals to itself is a common side that belongs to both triangles. So again, we found out that side EB equals to itself is a common side that belongs to both triangles. So we found out that all the three sides of this triangle EMB are corresponding equal to all the three sides of this triangle EBC, and therefore those two triangles can go into each other according to side rule. So until now, we found out that triangle EMB congruent, this is the side of congruent to triangle EBC according to side rule. And from the fact that those two triangles can go into each other, we will derive that they are also the same areas. That is to say, the area of this triangle EMB is equal to the area of this triangle EBC. It again, found out that the area of triangle EBM is equal to the area of triangle EBC because they can go into each other. In the next step, we find out the area of this triangle EBM. What is the area of triangle EBM? Here we know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of this triangle EBM will be equal to the base MB times the height EA over 2. And again, if you found out that the area of triangle EBM equals to the base MB times the height EA over 2. MB equals to 1 times EA. EA also equals to 1 divided by 2. So in total, we found out that the area of triangle EBM is equal to 1 times 1 over 2. 1 times 1 is 1 over 2. So now we found out that the area of triangle EBM is equal to 1 half square units in its size. So we can write here that the area of triangle EBM is equal to 1 half square units in its size. And for this equation, 1 half equals to the area of triangle EBM equals to the area of triangle EBC. We derive that the area of triangle EBC is also equal to 1 half square units in its size. Now because those two sides of the equation they are equal to each other. So the area of triangle EBC is also equal to 1 half square units in its size. In the next step we will focus on this big quadrangle EMBC. What is the area of this big quadrangle EMBC? Actually, the area of this big quadrangle EMBC must be equal to the sum of the areas of the shapes that it consists of. Quadrangle EMBC consists of those two shapes. Therefore, the area of quadrangle EMBC must be equal to the sum of the areas of those two shapes. The two shapes are actually triangle EMB and triangle EBC. And therefore, the area of the big quadrangle EMBC must be equal to the area of the first shape that it consists of, that is actually triangle EMB, plus the area of the second shape that it consists of, this is triangle EBC. And again, I should find out that the area of the big quadrangle EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is triangle EMB, plus the area of the second shape that it consists of, that is actually triangle EBC. But we already found out that this triangle EMB is equal to 1 half, plus the area of triangle EBC that also equals to 1 half. So in total, the area of the big quadrangle EMBC equals to 1 half plus 1 half, that is 1. So she found out that the area of the big quadrangle EMBC is equal to 1 square units in its size. From one side, but from the other side, you can look on the big quadrangle EMBC in a different way. We find out that quadrangle EMBC consists of two other shapes. And actually, the first shape that it consists of is this green right triangle EMA. The second shape that it consists of is this quadrangle ABCE. And therefore, the area of the big quadrangle EMBC must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to the area of the green triangle EMA, the green right triangle EMA, plus the area of this quadrangle ABCE. Do it again. The area of the big quadrangle EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the green right triangle EMA plus the area of quadrangle ABCE. And from this equation, 1 equals to the area of the big quadrangle EMBC equals to the area of the green right triangle EMA plus the area of quadrangle ABCE. Those two sides are equal to each other. Okay, those two sides are equal to each other, so we can write down that 1 equals to the area of the green right triangle EMA plus the area of quadrangle ABCE. And again, those two sides of the equation are equal, therefore 1 equals to the area of the green right triangle EMA plus the area of quadrangle ABCE. But according to our definition, the area of this green triangle EMA equals to Z coordinates inside. So we can substitute the area of triangle EMA by Z. Is equal to Z according to our definition. Z coordinates in size. So 1 equals to Z plus the area of quadrangle ABCE. And again, in total, we found out that Z plus the area of quadrangle ABCE equals to 1. Our task is to find out the area of this big pentagon ABCDE. So what's the area of pentagon ABCDE? And the task is to find out the area of the big pentagon ABCDE. Actually, the area of this big pentagon ABCDE must be equal to the sum of the areas of the shapes that it consists of. The big pentagon ABCD consists only those two shapes, and therefore the area of the big pentagon ABCD must be equal to the area of those two shapes that it consists of. It consists of those two shapes and not anymore. So the area of the big pentagon ABCD must be equal to the area of this green right triangle EDC plus the area of this quadrangle. The second shape that it consists of is this quadrangle ABCE. Read again. The area of the big pentagon ABCD must be equal to the sum of the areas of the two shapes that it consists of. It consists of only those two shapes and not anymore. The first shape is 1 equals to the area of the big pentagon ABCD plus the area of quadrangle ABCE. And again, in total, we found out that the area of the big pentagon ABCD must be equal to the sum of the areas of the two shapes that it consists of. It consists of only those two shapes and not anymore. the right triangle EDC. The second shape is quadrilateral ABC, and therefore the area of the big pentagon ABCD must be equal to the area of the first shape, that is the green right triangle EDC, plus the area of the second shape, that is quadrilateral ABCE. But we already found out that the area of this green triangle EDC equals to the square in its size. So we can write here that the area of the EDC equals to z square units in its size. We have to add here this plus the area of quadrilateral ABCE. So in total we found out that the area of the big pentagon ABCD is equal to Z plus the area of quadrilateral ABCE. But we already found out that Z plus the area of quadrilateral ABCE equals to 1. So we can write here that Z plus the area of quadrilateral ABC equals to 1. I copy this equation here. And from this long equation, we derive that the area of the big pentagon ABCD equals to 1. Square units. So the answer to the first question is that the area of this big pentagon ABCDE is equal to 1 square unit in its size. So we finished with the first question. In the next step, I present you the second question and solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. The green shape is actually triangle A and B. So we have to find out the area of the green triangle A and B. So it is given as a question that AB is the diameter of the circle. Chord AB is the diameter of the circle. So in addition, we know that those two angles are both right angles. PQ is a tangent to this circle, point M. Point M is the point of tendency of tangent PQ with this circle. In addition, we know that AP equals to 9, BQ equals to 4. Again, our task is to find out the area of this green shape, that is actually the green triangle A and B. So first of all, we can implement rule 7 in our drawing. So I please go to rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. Chord AB is the diameter of the circle. This is peripheral angle CB that subtends on the diameter of the circle, that is called AB, therefore is equal to 90 degrees in its size according to this rule, rule 7. So according to rule 7, any peripheral angle that subtends on the diameter of the circle, it must be equal to 90 degrees in its size. We can definitely implement rule 7 in our drawing. Why? Because in our drawing, we have peripheral angle A and B. Peripheral angle A and B subtend to the diameter of the circle, that is called AB, and therefore it must be equal to 90 degrees in its size according to rule 7. define this angle to the angle PAL as alpha. So in the right triangle APM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. PQ is a tangent to the circle at point M. So PQ is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to all three. All three states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PQ at point M? We have this angle is equal to 90 degrees minus alpha plus this angle to this right angle plus this missing angle to the angle BMQ. In total, those three angles must be equal to 180 degrees according to all three. So I will write it down. 90 degrees minus alpha plus 90 degrees plus the third missing angle to the angle BMQ. In total, the sum of those three angles must be equal to 180 degrees according to all three. Ninety degrees plus 90 degrees is 180 degrees plus the missing angle BMQ minus alpha is equal to 180 degrees. So here we have 180 degrees on both sides of this equation, so 180 degrees will get cancelled, and we have to only if the missing angle BMQ minus alpha equals to 0. Here we add alpha to this equation and finally get that the missing angle BMQ is equal to alpha degrees in its size. This is the missing angle BMQ is equal to alpha degrees in its size. So in this small right triangle BMQ, this angle equals to alpha. This angle equals to 90 degrees, and therefore this furthest angle must be equal to 90 degrees minus alpha, according to the rule that says that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we prove that those two right triangles can go into each other according to angle similar to. That is to say, the big right triangle APM can go into this small right triangle BMQ according to angle similar to. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So we should find out that all the figures of this big right triangle APM corresponding equal to all the figures of this right triangle BMQ. Therefore, those two right triangles can go into, are similar to each other according to angle similar to. So right now, we should find out that the big right triangle APM is similar. This is the sign of similar to the small right triangle BMQ according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side AP of the big right triangle APM, or side MQ of the small right triangle BMQ, is equal to side PM of the big right triangle APM, or side BQ of the small right triangle BMQ. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. AP is 9 over MQ. MQ is the missing side, so we notice it is. And it is equal to PM. PM is the missing side, so we notice it is. Over BQ. BQ is 4, according to what is given the question. So in total, I should find out that 9 over MQ equals to PM over 4. Here we will cross multiply this equation, and we get that PM times MQ is equal to 9 times 4, that is 36. And again, I should find out that PM times MQ equals to 36. In the next step, to define the center of this circle, this point is point O. So, we define the radius of this circle as R. So, OA is R, is the radius of the circle that is equal to R. OB is also the radius of the circle that is equal to R according to our definition. In the next step, we will join points O and M together by a straight line. Point M is the point of tendency of tangent PQ with this circle. Point O is the center of the circle. Point M is the point of the circle itself. So for OM is the radius of this circle is equals to R according to our definition. The radius OM that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent PQ with this circle. And whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we'll do a construction, that is to say, from point O, that is the center of the circle, we'll go perpendicular on side AP. Again, from point O, we'll go perpendicular on side AP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We'll define the touching point of the perpendicular from point O inside AP. This point is point L. By doing this construction, we can deduce the big quadrilateral LOMP. Inside the big quadrilateral LOMP, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees. According to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its side. So, in quadrilateral LOMP we have 4 rectangles. In quadrilateral LOMP we have 4 rectangles. And therefore, according to rule 5, any quadrilateral that has 4 right angles must be if there's a rectangle, if not a square. So let's quadrilateral LOMP is a rectangle because it has 4 right angles. In the next step, we will do another construction, that is to say, from point B, we will go perpendicular on the radius OM. Again, from point B, we will go perpendicular on the radius OM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in the radius OM. This point is point S. By doing this construction, we created the small quadrilateral SBQM. Inside the small quadrilateral SBQM, we have 1, 2, 3 rectangles. And therefore, this fourth missing angle must be equal to 90 degrees in its size. And therefore, the small quadrilateral SBQM is a rectangle according to rule 5 because it has 4 right angles. In the next step, we focus on the big rectangle LOMP. We know that the opposite sides of a rectangle are parallel to each other. So in rectangle LOMP, side LP is parallel to the opposite side OM. But LP is part of the straight line AP. Again, LP is part of the straight line AP. So if a part of the straight line is parallel to another straight line, then the straight line AP itself must be also parallel to the other straight line OM. Therefore, AP is parallel to OM. If you follow that AP is parallel to the radius OM. In the next step, I'll copy the two parallel lines AP and OM and also the diameter AOB in a new page, and we will implement rule 50 in the new drawing. Okay, those are the two parallel lines AP and OM. AOB is the diameter of the circle. Those two angles are defined as corresponding angles and they are located between the parallel lines AP and OM, and therefore they are equal to each other. They are equal to each other according to rule 50. So repeat quickly rule 50. According to rule 50, corresponding angles between parallel lines are equal to each other. In the drawing, you have line A that is parallel to line B. The red line C cuts those two parallel lines at those 2 points. Those two angles are defined, those two angles alpha and beta are defined as corresponding angles, and they are located between the power lines A and B, and therefore they are equal to each other in their sizes. That is to say, alpha equals to beta. So we can implement all 50 in our drawing. In our drawing, we have those two corresponding angles that are located between the two power lines A, P, and OM, and therefore they are equal to each other in their sizes according to rule 50. So if you define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to rule 50. So if you found out that angle PAO equals to beta, this is angle PAO is equals to beta. And again, this is angle PAO, the big angle, is equal to beta. In addition, also found out that angle MOB also equals to beta. This is angle MOB, it is also equals to beta. So in this green right triangle, this angle equals to beta. This green right triangle OSB, this angle equals to beta, this angle equals to 90 degrees, and therefore this red missing angle must be equal to 90 degrees minus beta. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the upper right triangle AOL, this angle equals to beta, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two right triangles can go into each other according to angle side angle rule. And again, we prove that the right triangle ALO can go into this right triangle OSB according to angle side angle rule. So we have to prove that the right triangle ALO can point to this lower right triangle OSB according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles, they are both equal to beta and therefore they are equal to each other. So this is angle LAO, in the right triangle ALO, and it is equal to this angle, that is actually angle MOB, it is actually angle SOB, in the right triangle SOB. And again, if you want to know that angle LAO in the right triangle ALO is equal to angle SOB in the right triangle SOB, they are both equal to beta and therefore they are equal to each other. In addition, side AO in the right triangle ALO is equal to side OB in the right triangle OSB. The above perimeter of the circle is equal to 1 and therefore they are equal to each other. And again, we should find out that side AO in the right triangle ALO is equal to side OB in the right triangle OSB. The above perimeter of the circle is equal to 1 and therefore they are equal to each other. And finally, those two angles they are both equal to 90 degrees, one is better and therefore they are equal to each other. So actually this is angle AOL in the right triangle ALO, and it is equal to this angle, the left angle OBS in the right triangle OSB. And again, I should find out that angle AOL is equal to angle OBS. Angle AOL in the right triangle ALO is equal to angle OBS in the right triangle OSB. They are both equal to 90 degrees, one is better, and therefore they are equal to each other. So if we found out that those two angles and the side that is included between those two angles in this right triangle ALO are corresponding equal to those two angles, and the side that is included between those two angles in this right triangle OSB. And therefore, those two right triangles can move into each other according to angle, slight angle rule. We have those two angles and the side that is included between those two angles in this triangle ALO corresponding equal to those two angles, and the side that is included between those two angles in this triangle OSB. And therefore, those two right triangles can move into each other according to angle, side angle rule. So, write it down. We should find out that the right triangle ALO congruent. This is the sign of congruent to the right triangle OSB according to angle, side angle rule. As for the fact that those two right triangles can move into each other, we derive that LO, side LO, the right triangle ALO is equal to side SB in the right triangle OSB. And again, we derive that LO equals to SB. So phi side LO equals to SB. Because of the fact that those two right triangles can move into each other, we have the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles can move into each other, and therefore those two corresponding sides, that is to say LO and SB, must be also equal to each other in their lengths. So if we define the length of this side LO as x, then the length of side SB must be also equal to x because they are equal to each other. You know that the opposite sides of a rectangle are equal to each other. So in the big rectangle LOMP, side LO must be equal to the opposite side PM. But LO equals to x, and therefore the opposite side PM must be also equal to x in its length. Likewise, in the small rectangle SBQM, side SB must be equal to the opposite side QM. But SB is x, therefore the opposite side QM must be also equal to x units in its length. We already found out that PM times MQ equals to 36. Okay, again. So we found out that PM times MQ equals to 36. PM is X, MQ is also X. PM equals to X, MQ also equals to X. MQ also equals to X. So PM times MQ is X times X, that is 36. So in total we found out that X times X equals to 36. X times X is X squared equals to 36. Here we take root out of this equation and finally get that X equals to the square root of 36, that is 6. So X equals to 6 units in its length. We have X equals to 6. And here also X equals to 6. In the next step, we will implement the Pythagoras theorem on this small right triangle BMQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the evaluation of Pythagoras theorem. So this small right triangle BMQ, according to the Pythagoras theorem, BM squared, that is the square of the hypotenuse, is equal to BQ squared plus MQ squared. And again, in small right triangle BMQ, according to the Pythagoras theorem, BM squared, that is the square of the hypotenuse, equals to BQ squared plus MQ squared. BM is the missing side, so we have to set it, so it is BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16. Plus MQ squared. MQ is 6, therefore MQ squared is 6 squared, that is 36. In total, we will know that BM squared equals to 16 plus 36. 16 plus 36 is 52. So BM squared equals to 52. Here we take out all of this equation and find again that BM, the missing hypotenuse BM, is equal to the square root of 52 units in its length. This side BM is equal to the square root of 52 units in its length. In the next step, we will implement the Pythagoras theorem on this big right triangle APM. Here by PT is the evaluation for Pythagoras theorem. According to the Pythagoras theorem, in this big right triangle APM, AM squared, that is the square of the hypotenuse, is equal to AP squared plus PM square. But again, the big material APM according to the also, we get that AM squared, this is the square they follows, equals to AP square plus PM square. AM is the missing side, so let us see it, so it is AM square equals to AP square. AP is 9, therefore AP square is 9 squared, it is 81. Plus PM square. PM is 6, therefore PM square is 6 squared, that is 36. So in total we found out that AM squared equals to 81 plus 36. 81 plus 36 is 117. So AM squared equals to 117. Here we take out all of this equation, and finally take out all of this equation, and finally we get that AM, the missing hypothesis AM, is equal to the square root of 117 units in its length. AM equals to the square root of 117 units in its length. Our test is to find out the area of this green shape. The green shape is actually the right green triangle AMP. The right green triangle AMB. So we have to find out the area of this right green triangle AMB. Note that the area of the triangle equals to the base of the triangle times the height over 2. We take the base as BM times the height AM over 2. So in total we found out that the area that we are looking for in this question, that is the area of the green shape, is equal to the area of the green right triangle AB, and the area of the green triangle AB equals to the base BM times the height AM over 2. We already found out that BM equals to the square root of 52 times the height AM. We already found out that the height AM is equal to the square root of 117 units in its length divided by 2. And again, the base BM is equal to the square root of 52 units. The height AM is equal to the square root of 117 units divided by 2. We have the algebraic identity. It says that the square root of A times the square root of B is equal to the square root of A times B. And again, the square root of A times the square root of B is equal to the square root of A times B. According to this algebraic identity, we get that the square root of 52 times the square root of 117 will be equal to the square root of 52 times 117 divided by 2. We have to divide it by 2. 52 times 117 is 6,084. So it is the square root of 6,084 divided by 2. The square root of 6,084 is 78 divided by 2. 78 over 2 is 39. So in total, we actually found out that the area of the green shape, that is the area that we are looking for in this question, is equal to 39 square units in its size. Then again, I should know that layer of this ring shape is equal to 39 square units in its size. So we finished with the second question. In the next step of some of the lecture, I'll start with the first question, of course. In the first question, our task is to find out the area of this pentagon ABCDE. What is a pentagon? A pentagon is a flat closed shape with 5 sides and 5 interangles. This is pentagon ABCDE. It has 5 sides, 1, 2, 3, 4, 5, and 5 interangles. 1, 2, 3, 4, 5. So, in the drawing, we have the big pentagon, this big pentagon ABCDE. In addition, we know that those two angles are both right angles. ED equals to EA equals to BC. They are both equal to 1. They are all equal to 1. Unit in their lengths. DC equals to x and AB equals to 1 minus x. Again, our task is to find out they have this big pentagon ABCDE. So first of all, we join points E and B together, and then we join points A and C together by a straight line. In the next step, we extended the straight line BA by a straight line in such a way that the extended part MA will be equal to x units in its length. But again, MA equals to x according to our construction. BA is one side of pentagon ABCDE, and therefore it is absolutely a straight line. So if we, when we extend a straight line by a straight line, the result BM is also a straight line. So BM is a straight line, so if you focus on the upper side of the straight line BM at point A, here the sum of the angles must be equal to 180 degrees according to all three. All three states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BM at point A? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. The next step, we join points E and M together by a straight line. By joining points E and M, we created the green right EAM. The next step, we put that those two green right triangles can go into each other according to side angle side rule. This is the green right EDC. So, why those two green right triangles can go into each other? First of all, those two sides are both equal to x and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides are both equal to 1 and therefore they are equal to each other. So we should prove that those two sides and the angle that is included between those two sides in this green triangle EAM are corresponding equal to those two sides and the angle that is included between those two sides in this green right triangle EDC. And therefore those two green right triangles can go into each other according to side angle side rule. We have those two sides and the angle that is included between those two sides in this green right triangle EAM are corresponding equal to those two sides and the angle that is included between those two sides in this green right triangle EDC. And therefore those two right triangles can go into each other according to side angle side rule. So the image we found out that the right triangle EAM can go into the right triangle EDC according to side against side rule. And from the fact that those two right triangles can go into each other, we derive two things. First of all, we derive the area of those two right triangles, they have the same areas. But why? Because any two triangles that can go into each other, they must have also the same areas. So actually, if we define the area of this right green triangle as Z, then the area of this green right triangle EDC must be also equal to Z squared in size because they have the same areas. And the second thing that we derive from the fact that those two right green triangles can go into each other, we derive that side EC of this right triangle EDC is equal to side EA of this green right triangle EMA. EC equals to EM. EC equals to EM according to the rule that corresponding sides in right triangles are equal to each other. Those two green right triangles can go into each other, and therefore those two corresponding sides must be also equal to each other in their lengths. In the next step, we calculated the length of this line segment MB or side MB. MB in total equals to MA plus AB. Again, MB equals to MA plus AB. MB equals to MA, that is x, plus AB, that is 1 minus x. So in total, MB equals to x plus 1 minus x. So x minus x is 0, so left only with 1. So in total, we found out that MB equals to 1 unit in its length. In the next step, we prove that those two triangles can go into each other according to side rule. That is to say, we prove that this triangle EMB can go into this triangle EBC according to side rule. So why those two triangles can go into each other? First of all, MB is equal to 1 equals to BC, that is also equals to 1. Those two sides are both equal to 1 and therefore they are equal to each other. In addition, we just find out that M equals to EC. And finally, EB is a common side that belongs to both triangles. EB belongs to triangle MEB and EB also belongs to triangle EBC. So EB equals to itself is a common side that belongs to both triangles. So if we prove that all the three sides of this triangle EMB are corresponding equal to all the three sides of this triangle EBC, and therefore those two triangles can go into each other according to side rule. And again, if we found out that triangle EMB can go, this is the side can go to triangle EBC according to side rule. And from the fact that those two triangles can go into each other, we derive that they have also the same areas. Okay, again, any two triangles that can go into each other must have also the same areas. So we conclude that the area of this triangle EMB is equal to the area of this triangle EBC. Again, we derive that the area of triangle EMB is equal to the area of triangle EBC. In the next step, we calculated the area of this triangle MEB. The area of any triangle equals to the base of the triangle times the height over 2. And therefore, the area of this triangle MEB must be equal to the base MB times the height AE over 2. Repeat again, the area of triangle MEB must be equal to the base MB times the height AE over 2. MB is 1, AE is also 1. So MB times EA is 1 times 1 divided by 2. 1 times 1 is 1 over 2. So total, we found out that the area of this side MEB is equal to 1/2 square units in its size. The area of MEB is equal to 1/2 square units in its size. So can I do that the area of MEB is equal to 1/2 square units in its size? And from this equation, 1/2 equals to the area of EMB equals to the area of EBC. We derive that the area of EBC is also equal to 1/2 square units in its size. Those two sides of this equation are equal to each other. Therefore, the area of EBC is also equals to 1/2 square units in its size. The area of EBC is equal to 1/2 square units in its size. In the next step, we focus on this big quadrangle EMBC. What is the area of this big quadrangle EMBC? Actually, the area of quadrilateral EMBC must be equal to the sum of the areas of the shapes that it consists of. The big quadrilateral EMBC consists of those two shapes. Therefore, the area of quadrilateral EMBC must be equal to the sum of the areas of those two shapes. The first shape is triangle EMB and the second shape is triangle EBC. And therefore, in total, the area of the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. The first shape is triangle EMB, so it is the area of triangle EMB, and the second shape is triangle EBC, so plus the area of triangle EBC. We already found out that the area of triangle EMB, the area of triangle EMB equals to 1/2 square units in size, and the area of triangle EBC is also equal to 1/2 square units in size. So in total, the area of triangle EMB plus the area of triangle EBC equals to 1/2 plus 1/2, that is 1. So in total, we found out that the area of the big quadrilateral EMBC is equal to 1 square unit in its size. From one side, but from the other side, you can look in on the big quadrilateral EMBC in a different way, and we find out that the big quadrilateral EMBC consists of two other shapes. The big quadrilateral EMBC consists of this green rectangle EMA, and the second shape that it consists of this quadrilateral ABCE. And therefore, the area of the big quadrilateral EMBC must be equal to the sum of the areas of those two shapes that it consists of. And again, the area of the big quadrilateral EMBC must be equal to the first shape that it consists of, that is triangle EMA, therefore it is the area of triangle EMA, plus the area of the second shape that it consists of, that is quadrilateral ABCE, so plus the area of quadrilateral ABCE. So in total, we should all know that 1 equals to the area of the big quadrilateral EMBC equals to the area of triangle EMA plus the area of quadrilateral ABCE. And from this local equation, we derive that those two sides of this local equation, they are equal to each other. Those two sides are equal to each other. That is to say, 1 equals to the area of triangle EMA plus the area of quadrilateral ABCE. Again, 1 equals to the area of triangle EMA plus the area of triangle ABCE. But according to our definition, the area of this triangle EMA equals to Z square units in size. So you can substitute the area of triangle EMA by Z and get that 1 equals to Z plus the area of quadrilateral ABCE. And again, 1 equals to Z plus the area of quadrilateral ABCE. Our task is to find out the area of this big pentagon ABCE. So what is the area of the big pentagon ABCE? Actually, the area of the big pentagon ABCE must be equal to the sum of the areas of the sum of the areas of the shapes that it consists of. The big quadrilateral ABCE consists of only those two shapes and not anymore. And therefore, the area of the big quadrilateral ABCD must be equal to the area of this shape plus the area of the second shape. The first shape is the green rectangle EDC and the second shape is quadrilateral ABCE. And therefore, in total, the area of the big pentagon ABCDE is equal to the sum of the two shapes that it consists of. This is to say it must be equal to the area of the green rectangle EDC plus the area of quadrilateral ABCE. We already found out that the area of this green rectangle EDC is equal to Z square units in size. So we can substitute the area of triangle EDC by Z. And look to it here, quadrilateral, the area of quadrilateral ABC. Copy this quadrilateral here. So in total, we found out that the area of the big pentagon ABCD equals to Z plus the area of quadrilateral ABCE. But we already found out that Z plus quadrilateral ABC equals to 1. So you can write here that Z plus the area of quadrilateral ABC equals to 1. I copy this equation here. And from this long equation, we derive that the area of the big pentagon ABCD is equal to 1 square units in size. of the big pentahedral ABCD equals to 1 square in size. And again, if you found out that the area that you are looking for this question, that is the area of this big pentahedral ABCD is equal to 1 square in size. So we finish with the first question. In the next step, I'll repeat on the solution for the second question. Our task in the second question is to find out the area of this green shape. The green shape is actually the green triangle A and B. So the task is to find out the area of this green triangle A and B. This gives us a question that AB is the diameter of this circle. In addition, we know that those two angles are both right angles. AP equals to 9, BQ equals to 4. PQ is the tangent of this circle, it's point M. Point M is the point of tendency of tangent PQ with this circle. Again, our task is to find out the area of this green shape, that is actually the green triangle A and B. So first of all, we can implement rule 7 in our drawing. Why? Because according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in size. This is peripheral angle A and B that subtends on the diameter of the circle, that is called AB, and therefore must be equal to 90 degrees in size according to rule 7. In the next step, we define angle PAM. This angle is alpha. So in the right triangle APM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. PQ is the tangent of the circle at point M, so PQ as a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line PQ at point M? We have this angle is equal to 90 degrees minus alpha, plus this angle is equal to 90 degrees according to rule 7, plus this piece angle BMQ. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. So if you follow that 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ must be equal to 180 degrees according to rule 3. 90 degrees plus 90 degrees is 180 degrees, plus the missing angle BMQ minus alpha equals to 180 degrees. Here we have 180 degrees on both sides of the equation, so 180 degrees will get cancelled, and left only with the missing angle BMQ minus alpha equals to 0. Here we add alpha to this equation, and we found out that the missing angle BMQ equals to alpha degrees in size. This is the missing angle BMQ, is equal to alpha degrees in its size. So in the small right triangle BMQ, this angle equals to alpha. This angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha according to the rule that says that the sum of the angles in a triangle is equal to 180 degrees. The next step, we put that those two right triangles are similar to each other according to angle similarity rule. That is to say, we put that the big right triangle APM is similar to this small right triangle BMQ according to angle similarity rule. That is to say, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you prove that all the angles of this big right triangle APM are corresponding equal to all the angles of this big right triangle BMQ. Therefore, those two right triangles are similar to each other according to angle similarity rule. Because again, if you know that the big right triangle APM is similar, this is the same similar to the small right triangle BMQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side AP of this big right triangle APM or side MQ of this small right triangle BMQ is equal to side PM of this right triangle APM or side BQ of this right triangle BMQ. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. AP is 9, over MQ. MQ is the missing side, so limited cities, and it is equal to PM. PM is also the missing side, so limited cities, over BQ. BQ is 4. So in total, if you found out that 9 over MQ equals to PM over 4. Here we cross multiply this equation, and we found out that PM times MQ equals to 9 times 4, that is 36. Okay, there we found out that PM times MQ equals to 36. In the next step, we define the center of this circle. This point is point O. And we also define the radius of this circle as R. So OA is the radius of the circle that is equal to R, and OB is also the radius of the circle that is equal to R. In the next step, we join points O and M together by straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that is equal to R. Point M is the point of tendency of tangent PQ with this circle. The radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent PQ with this circle. And whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did the construction, that is to say from point O, that is the center of the circle, we go perpendicular on side AP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O in AP. This point is point L. By doing this construction, we created the big quadrilateral LOMP. Inside the big quadrilateral LOMP, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 450 angle, total the mass is equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 450 angle must be equal to 90 degrees in its size. So inside the big quadrilateral LOMP, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be in this rectangle Francisco. So we write to this big quadrilateral LOMP is a rectangle because it has 4 right angles. In the next step, we did another construction, that is to say from point B we go perpendicular on the radius OM. Again, from point B we go perpendicular on the radius OM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and the radius OM. This point is point S. By doing this construction, we created the small quadrilateral SBQM. Inside the small quadrilateral SBQM, we have 1, 2, 3 right angles, and therefore this 450 angle must be equal to 90 degrees in size. And therefore quadrilateral SBQM is rectangle because it has 4 right angles. The next step we focus on this rectangle LPMO. We know that the opposite sides of rectangle are parallel to each other. So in rectangle LPLO, side LP must be equal to side LP must be parallel to the opposite side OM. So LP is parallel to OM. If LP, so and we know that AP is LP is part of the straight line AP. Again, LP is part of the straight line AP. If a part of the straight line is parallel to another straight line, then the straight line AP itself must be also parallel to the other straight line OM. So in total, we should find out that AP is parallel to OM. AP is parallel to OM. In the next step, I copy those two parallel lines, AP and OM, and the diameter AOB. In the page, we plotted rule 50 on the new drawing. Here, this is line AP, this is parallel to line OM. This is the diameter AOB. Those two angles are defined as corresponding angles and are located between the parallel lines AP and OM, and therefore they are equal to each other according to rule 50. Rule 50 states that corresponding angles between parallel lines are equal to each other. So those two corresponding angles are located between the parallel lines AP and OM, and therefore they must be equal to each other in their sizes. So if you define the size of this angle as beta, then the size of this angle must be also equal to beta, because they are equal to each other according to rule 50. So if you found out that angle PAO equals to beta, this is angle PAO is equal to beta. And I also found out that angle MOB also equals to beta. This is angle MOB, this is also equal to beta. So In the small green triangle SOB, this angle equals to beta, this angle equals to 9 degrees, and therefore this first angle must be equal to 9 degrees minus beta, according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the upper right triangle LOA, this angle equals to beta, this angle equals to 9 degrees, and therefore this first angle must be equal to 9 degrees minus beta, according to the sum rule that said that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we put that those two right triangles can go into each other according to angle side angle rule. While those two right triangles, this is the right triangle ALO, is can go into the right triangle OSB according to angle side angle rule. So while those two right triangles can go into each other. First of all, those two angles are both equal to beta, and therefore they are equal to each other. In addition, side AO of triangle ALO is equal to side OB of triangle OSB. They are both the area of the circle is equal to R, therefore they are equal to each other. And finally, those two angles, they are both equal to 9 degrees minus beta, and therefore they are equal to each other. So if you found out that those two angles and the side that is included between those two angles, this right triangle ALO correspondingly equal to those two angles, and the side that is included between those two angles, this right triangle OSB. And therefore, those two right triangles can go into each other according to angle side angle rule. We have those two angles and the side that is included between those two angles in this right triangle ALO corresponding equal to those two angles, and the side that is included between those two angles in this right triangle OSB. And therefore, those two right triangles can go into each other according to angle side angle rule. At the end, if you found out that the right triangle ALO can go into the right triangle OSB according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that LO equals to SB. LO equals to SB. LO equals to SB according to the rule that says that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides, that is to say LO and SB, must be also equal to each other in their lengths. So if you define the length of LO is x, then SB must be also equal to x because they are equal to each other. So in the big rectangle LOMP, the opposite sides are equal to each other. That is to say, side LO is equal to the opposite side PM, but LO is x, therefore PM must be also equal to x. Likewise, in the small rectangle SBQM, side SB must be equal to the opposite side MQ. But SB is x, therefore the opposite side MQ must be also equal to x units in its length. We already found out that PM times MQ equals to 36. PM is x, MQ is also x. So here PM is x and MQ is x is equals to 36. So x times x equals to 36. X times x is x squared is equals to 36. Here we took out all of this equation and we found out that x equals to the square root of 36, that is 6. Here x equals to 6 and here also x equals to 6. In the next step, we implemented the Pythagoras theorem on this small right triangle BMQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the small right triangle BMQ, BM squared is the square of the hypotenuse equals to BQ squared plus MQ squared. And again, the small right triangle BMQ, according to the Pythagoras theorem, BM squared is the square of the hypotenuse equals to BQ squared plus MQ squared. BM is the missing side, so leave this it is, so it is BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, it is 16. Plus MQ squared. MQ is 6, MQ is 6, therefore MQ squared is 6 squared, it is 36. So in total, we shall know that BM squared equals to 16 plus 36. 16 plus 36 is 52, so BM squared equals to 52. Here we took out of this equation and found out that BM equals to the square root of 52 units in its length. This is side BM, this equals to the square root of 52 units in its length. In the next step, we implemented the Pythagoras theorem in this big right triangle APM. According to the Pythagoras theorem in the big right triangle APM, AM squared is the square of the hypotenuse equals to AP squared plus PM squared. And again, the big right triangle APM, according to the Pythagoras theorem, AM squared is the square of the hypotenuse equals to AP squared plus PM squared. AM is the missing side, so leave this it is, and it is equals to AP squared. AP is 9, therefore AP squared is 9 squared, that is 81. Plus PM squared. PM is 6, therefore PM squared is 36. So in total, if you want to know that AM square equals to 81 plus 36. 81 plus 36 is 117. So AM square equals to 117. We have to go out of the equation and find out that AM equals to the square root of 117 units in its length. This is side AM, this equals to the square root of 117 units in its length. Our task is to find out the area of this green shape. The green shape is actually the green right triangle A and B. So we have to find out the area of the green right triangle A and B. The area of the green triangle A and B must be equal to the base MB times the height MA over 2. Again, our test is to find out the area of the green shape. It is equal to the area of the green right triangle A and B. The area of the green triangle A and B will be equal to the base BM times the height AM times the height AM over 2. AM is square root of 52 units in its length. MB is square root of 52 units in its length. AM is the square root of 117 units in its length. Again, BM is square root of 52, AM is square root of 117, divided by 2. So in total, the area of the green shape equals to the square root of 52 times the square root of 117 over 2. We have the algebraic identity that says that the square root of A times the square root of B equals to the square root of A times B. So according to this algebraic identity, we get that the square root of 52 times the square root of 117 is equal to the square root of 52 times 117. And we have to divide it by 2. 52 times 117 is 6084. So in total, if you follow the area of the green shape equals to the square root of 6084 over 2. The square root of 6084 is 78, and we have to divide it by 2. 78 over 2 is 39. So in total, we should follow that we are looking for this question, that is the area of the green shape equals to 39 square units in size. Until again, the area of this green shape is equal to 39 square units in size. Okay, thank you very much.